So I'm very happy to invite Professor Igor Rapinchuk of Michigan State University. He will be speaking on the local global principles for reductive groups or finitely generated groups. Professor Rapinchuk.
Okay. First, a big thank you to the organizers for the opportunity to speak in this special program. And I'm sorry I couldn't join in person, but at least we have Zoom these days. And I'd like to express my special thanks to Gopal Prasad for his help and inspiration over the years. And on a personal note, I've been very fortunate to know Gopal and his family for over 30 years, and I'm very thankful for that. Okay, so let me get started. So, as my title indicates, I'll be talking about local global principles for algebraic groups. But in order to motivate the discussion, I would first like to revisit a couple of classical results of algebraic number theory. And then by working through various reformulations, we'll gradually build up to local global principles for algebraic groups. And that'll be our main focus for today. Okay. So in this discussion, our setup will be as follows. So we'll take K to be a number field, V to be the set of all places of K, and by KV, we'll denote the completion of K at a place V. So the first result that I'd like to recall is the famous Hasse norm theorem, which tells us the following. So suppose we take a cyclic extension L over K, then an element of K star is a norm from L if and only if, when we view it as an element of the completion, it's a norm from the corresponding local extension for all V in V. So we can reformulate this like this. So basically, what the theorem is saying is that if we have a cyclic extension L over K, then the quotient of K star by the norm group coming from L injects into the product of the corresponding local quotients for all V in V. Now, when we formulate the theorem in this way, we can also interpret it in the language of division algebras. So, namely, recall that if we have any cyclic extension T over F, then this quotient group that we had on the previous slide, F star mod the norm group, is precisely the relative Brouwer group corresponding to our cyclic extension T over F. So therefore, from this point of view, what the Hasse norm theorem tells us is that the natural map from the global relative Brouwer group of L over K injects into the product of all of the local relative Brouwer groups. And this is true for any cyclic extension L over K. So of course, for division algebras, we have a far stronger result, namely the Albert-Brouwer-Hasse-Noether theorem, which tells us that the whole Brouwer group, whole global Brouwer group, injects into the product of all of the local Brouwer groups. Okay, so we have these two results. Now, these two theorems, so the Hasse norm theorem and the Albert-Brouwer-Hasse-Noether theorem, they're two fundamental results of global class field theory. And initially, when the subject was being developed, people thought about these results in very concrete terms. So specifically in terms of norms or division algebras. But then a bit later, primarily due to the work of Arden and Tate, global class field theory was reformulated in cohomological terms. And nowadays, it's more common to view these results as certain statements about cohomology. So recall that if we have any cyclic extension P over F, then basically by definition, the zeroth Tate cohomology group is precisely the quotient of F star by the norm group, so the object that we were considering on the previous slide. And furthermore, by the periodicity of cohomology of cyclic groups, Tate H0 is isomorphic to H2. So from this point of view, what the Hasse norm theorem tells us is that the natural global to local maps are injective on Tate H0 and Tate H2. Now, furthermore, if we recall that the Brauer group can also be described cohomologically as the second cohomology group of F with coefficients in F sub star, then the Albert-Brauer-Hasse-Noether theorem tells us that the corresponding global to local map is injective on H2. So the point here is that both of these results, the Hasse norm theorem and the Albert-Brauer-Hasse-Noether theorem, can be interpreted as cohomological local global principles. Now, we can actually push the cohomological perspective a bit further and interpret both results in the general context of the Galois cohomology of algebraic groups. So this is a bit more straightforward for the Hasse norm theorem, so let us start with that. So for that, we recall that if we have any finite separable extension, then we can associate to it a certain algebraic group called a norm torus. So this is a group defined over F with a property that its F points are precisely the elements of P of norm 1. And then using, for example, Shapiro's lemma and Hilbert's theorem 90, it's straightforward to show that the first Galois cohomology group of this algebraic group is precisely the quotient of S star by the norm. So using this interpretation, we see what the Hasse norm theorem tells us is that the natural global to local map on H1 of K with coefficients in this norm torus is injective for any cyclic extension of number fields. Okay, so now to go further, and in particular to interpret the Albert-Brauer-Hasse-Noether theorem in these terms, we need to consider the cohomology of possibly non-commutative algebraic groups. Okay, so this is quite a big subject in its own right. So let me not go into too much detail, but let's just recall the basic definitions. So first, if we have any field F and an algebraic group G defined over that field, we define the first Galois cohomology set of F with coefficients in G as the set of continuous one cocycles of the absolute Galois group of our field with values in the separable points of G modulo an appropriate equivalence relation. And so this definition is constructed in such a way that if G is a commutative algebraic group, then we recover precisely the usual first Galois cohomology group. But the point is that for general non-commutative algebraic groups, these objects are usually not groups, but only pointed sets. Okay, so these things carry far less structure and generally far less information than the commutative case, but they're still extremely useful. One reason being that it's often possible to interpret these Galois cohomology sets in terms of twisted forms of appropriate algebraic objects. Okay, so without going into all the formalism of twisted forms, let's just see what this means in the particular case when our group is PGLN. Okay, so by the Skolem-Noether theorem, we can identify PGLN with a group of algebra automorphisms of the matrix algebra MNF. Also, it's known that if we have a central simple algebra A over F of degree n, then over the separable closure, it becomes isomorphic to the matrix algebra. And using these considerations, one shows that the first Galois cohomology set of F with coefficients in PGLN can be identified with the isomorphism classes of simple algebras A over F having degree n. Okay, so we have this interpretation. And then returning to the Albert-Brouwer-Hasse-Noether theorem, in this language, what it implies is that for any number field K, the natural global to local map on H1 of PGLN is injective. Okay, so we've successfully reinterpreted our theorem about division algebras as a cohomological local global principle for the group PGLN. Now, maybe to give a little, more illustration of how these things go, let's look at another very similar example. So let's take F to be an n-dimensional non-degenerate quadratic form over field F. And I guess here I really should assume that F is of characteristic different from 2, but all of my fields are basically of characteristic 0 in this talk. Okay, so then, well, the isometry group of our quadratic form is, of course, the orthogonal group. And furthermore, any two such forms become equivalent over the separable closure. So putting these things together, we see that the first Gopal cohomology of F with coefficients in the orthogonal group corresponds precisely to the equivalence classes of non-degenerate quadratic forms F prime, which have dimension n. And so then, using this interpretation, we see that the classical Hasse-Minkowski theorem, which I recall tells us that two forms over a number field are equivalent, if and only if they're equivalent over all the completions of the number field. So this theorem can be phrased as saying that the natural global to local map of H1 with coefficients in the orthogonal group is injective. Okay, so the point is that this perspective, this cohomological perspective is extremely useful. So in particular, it allows us to rephrase various classical results in a kind of a uniform way. So this suggests that these kinds of issues are worth looking at in a rather general setting. And so for such questions, the typical setup looks like this. So we take K to be a field, V to be a set of rank 1 valuations of K. Again, we denote by KV the completion of K at V. And we take G to be an algebraic group over K. So then we say that the cohomological local global principle, or Hasse principle, holds if the natural global to local map is injective. And in this setting, it's also useful to define the corresponding Tate-Shafarevich set as the kernel of this global to local map. Now, one word of caution here is that, of course, if the Hasse principle holds, that is to say this map is injective, then, of course, the Tate-Shafarevich set is trivial. But the thing is, generally speaking, as I already mentioned, these things that we're dealing with are not groups. So just knowing that the Tate-Shafarevich set is trivial is typically not enough to conclude that the map is injective, and usually requires some additional considerations based on twisting. But in any case, so this is the general setup that one uses in the study of cohomological local global principles. And so just briefly returning to our previous discussion, so if we take K to be a number field and V to be the set of all places, we have seen in the examples in the previous few slides that the Hasse principle holds, for example, for the norm torus, corresponding to a cyclic extension for the group PGLN, or the orthogonal group. And quite generally, it's one of the fundamental results of the arithmetic theory of algebraic groups. It is known that the Hasse principle holds for any simply connected or adjoint algebraic group over a number field. Okay, so this is the situation over number fields. Now, another situation that has received quite a bit of attention over the last 10, 15 years or so is the following. So one takes K to be the function field of a curve over a p-adic base field, and V to be the set of all discrete valuations of K. Then, by work of Parimala, Suresh, Priti, and Hu, it's known that the Hasse principle holds for all simply connected groups of classical types, and it's conjectured to hold for all simply connected groups. Okay, so in other words, it is known that the Hasse principle holds in quite a lot of situations. But it would be a mistake to try to conclude from this that the Hasse principle always holds. And in fact, I mean, the Hasse principle fails already for groups, arbitrary linear algebraic groups, even over number fields. And actually, Serre gives some concrete examples of this failure in his book on Galois cohomology. So, but the situation, at least over number fields, is not so bad. So even though the Hasse principle may fail, it turns out that the deviation from the Hasse principle is always finite. So more precisely, it is known that the global to local map is proper. And in particular, this means that the Tate-Shafarevich set is finite. And so what our recent work suggests is that this properness property should hold in far greater generality, namely for reductive groups over arbitrary finely generated fields with respect to what are called divisorial sets of places. Okay, so I'd like to explain this last bullet point in a bit more detail now. So any questions at this point?
I think not.
Okay, so I'll just continue. Okay, so let me first say a few words about these divisorial sets of valuations. Okay, so we take K to be a finely generated field. Then we pick a model, script X, of our field K. So by definition, this is a normal integral. Well, we can take it to be an affine scheme over Z, whose function field is our finely generated field K. And then we consider the set of discrete valuations of K associated with the prime divisors on our model. So this is the divisorial set corresponding to our model X. Okay, so this is the sort of the geometric version of the construction. But if you prefer, and in fact, it's often useful to do this, we can view this construction in purely algebraic terms. And so it looks like this. So picking a model for our field basically amounts to finding a subring R of K, whose fraction field is the field K, such that R is a finely generated algebra over Z, or Fp, and R is integrally closed in K. And then the valuations correspond precisely to the height 1 prime ideals of our ring R. Okay, so to make this a little more concrete, let's just look at an example. And to keep things as sort of down to earth as possible, let's take the field of rational functions in one variable over Q. And for our subring, let's just take Z box X. So it's known that for this ring, the prime ideals of height 1 are principal, and they come in two types. So first, we have the ideals generated by the irreducible polynomials of content 1. And secondly, we have the prime ideals generated just by prime numbers. And so for each type of ideal, we have the corresponding discrete valuations. So the first set is usually called the geometric places. The second set is the arithmetic places. And then the union of these two sets, V0 and V1, is precisely the divisorial set of discrete valuations associated with our model spec R. Okay, so this is roughly speaking what these divisorial sets of places look like. So then, returning to this properness statement that I briefly mentioned a couple slides back. Okay, so we take K to be a finely generated field and V to be a divisorial set of places. And so then our expectation is that the global to local map should be proper for any reductive algebraic group of our finely generated field K. Well, at least, in good characteristic. And so in particular, this would imply that the Tate-Shafarevich set is finite. Okay, so far work on this conjecture has divided quite naturally into two rather distinct problems. So we have tori and semi-simple groups. So as we'll see in the next section, this conjecture is true for algebraic tori over arbitrary finely generated fields. Now, for semi-simple groups, the conjecture over general fields is still very much open. However, we've already obtained quite a number of results over so-called two-dimensional global fields. So that is to say, function fields of curves over number fields, as well in some other cases. And besides these specific results, the larger conceptual point turns out that for semi-simple adjoint groups, this conjecture, the properness conjecture, is closely related to the analysis of groups with good reduction. And so this is a topic that I'll talk about a little later in my talk. Okay, so any questions?
No, I think. Yes, one question. I think he can't hear you. One minute. Can hear you only through a mic.
My question was, do these Tate-Shafarevich sets in this case have any natural pairings on them, comparable to the Castle's pairing?
Well, so off the top of my head, my guess would be no. I mean, these things don't, have much of a group structure. So probably no, but this is something that I would have to think about a little. I don't really have a good answer off the top of my head.
Okay, thank you. Please go ahead.
Okay, so let me talk about this properness conjecture for algebraic tori now. Okay, so as I said, the conjecture has been settled for tori, and the precise result looks as follows. So suppose K is a finely generated field and V is a divisorial set of places. Then we show that the global to local map for any torus T, K torus T, is proper. And well, equivalently, since we're dealing with a commutative algebraic group in this statement, an equivalent way of formulating this is that the Tate-Shafarevich group is finite. Now, one remark is that, I formulated our conjecture only for connected reductive groups, and so therefore I've stated the theorem just for tori. But in fact, more generally, we've shown that the properness statement holds for any possibly non-commutative algebraic group whose connected component is a torus. Now, over number fields, the finiteness of the Tate-Charfaridge set is, of course, a well-known result. But the point is that the classical proof relies on Tate-Nakayama duality, which, of course, is not available over arbitrary finely generated fields. Now, the proof that we give uses adelic considerations. And in particular, what it implies is that the finiteness of the Tate-Charfaridge group for a torus over a number field actually follows from two classical statements of algebraic number theory, namely the finiteness of the class number and the finite generation of the group of units. And so to give a flavor of, of the proof, I would like to go through the argument for number fields and then indicate the modifications that are needed to handle arbitrary finely generated fields. Now, as I said, our proof uses adelic techniques. So I'd like to say a few words about adels in this setting. And I apologize if this is, sort of being pedantic and repetitive. But the point is that, adels are, of course, used widely in the study of algebraic groups over number fields, but they appear far less frequently in the setting of arbitrary finely generated fields. So I would just briefly like to recall the relevant notations and terminology just to make sure that we're all on the same page. Okay, so we take K to be a field, which we assume to be equipped with a set of discrete valuations, having the property that any element of our field is a unit at almost all places in V. And so this is, of course, a rather natural assumption, which will certainly hold in all examples that are relevant for us in this talk. Now, if we have such a set V, we can consider the corresponding Picard group. So by definition, this is the group of divisors, that is to say the free abelian group on V, modulo the subgroup of so-called principal divisors. So for example, if we're working with a number field K, and we take V to be the set of all finite places, then this Picard group is nothing more than the class group of the ring of integers. Okay, so then if we have our field K equipped with such a set V, we define the ring of adels as the restricted product of the completions with respect to the valuation rings. And of course, the group of edels is just the group of invertible elements of this ring. So one also defines the subring of integral edels and subgroup of integral edels in the usual way. And well, recall that we're assuming our condition star, which is to say that any element is a unit with respect to almost all places. So this means that K embeds into the adel ring and K star embeds into the adel group. So in particular, the adel ring has the natural structure of a K algebra. And furthermore, we have a natural map from the adel group to the group of divisors, which in particular allows us to identify the Picard group with the quotient of the adel group modulo the integral edels times the principal edels. Now, these constructions, just as in the classical case of number fields, they behave well with respect to finite field extensions. So namely, if we take L over K to be a finite field extension and V bar to be the set of all extensions of valuations in V to L, then the adel ring of L with respect to the set V bar is obtained just by basically extension of scalars to L. So in particular, if we consider a Galois extension, then the adel ring over L acquires a natural Galois action. Now turning more to algebraic groups, so if we have a K torus T, Then for each V and V, we denote by TOV the unique maximal bounded subgroup. Now, as I said earlier, the Adel ring has a natural structure of a K algebra, so therefore we can consider the points of T over this Adel ring. And this can be described quite concretely simply as the restricted product of the local points of T over all the completions with respect to these maximal bounded subgroups. So again, we have the subgroup of integral Adels, we have the diagonal embedding. Again, we can define things for a finite field extension L over K in basically the same way as before. In particular, if we're dealing with a Galois extension, then the group of adelic points acquires a Galois action. And furthermore, the diagonal embedding induces a map on H1, which will be important for us in just a little bit. Okay, so that's just a quick overview of the adelic setup. Again, as I said, just to make sure that we're all on the same page. Okay, so now let us briefly look at the argument for number fields. Okay, so we take K to be a number field, V to be the set of all places of K, T at a K torus, and we also fix a finite Galois splitting field, L over K. And so recall our goal is to show that the Tate-Shafarevich group of T with respect to the set V is finite. Okay, so the argument starts with two fairly standard reduction steps. So first, using Hilbert's theorem 90, one shows that the Tate-Shafarevich set can be identified, or Tate-Shafarevich group, sorry, can be identified with a relative Tate-Shafarevich group. So corresponding to this splitting field L over K. And secondly, one shows that this relative Tate-Shafarevich group can be identified with a kernel of this map-on cohomology that we had on the previous slide, arising from the diagonal embedding. And the point here, and this will be important for us a little later, is that both steps work over any field. So here we're not at all using the fact that we're working over a number field. Now, in the next step, we do need to use our assumption that K is a number field. So what one shows is that after possibly removing a finite number of places from V, we can write the Adel group as the product of the integral Adels times the principal Adels. So the point here is that, well, L is, of course, a number field, so its class group is finite. So therefore, we can find a finite set of places such that if we consider the corresponding ring of S integers or S bar integers, then the class group becomes trivial, right? But remember, the class group is precisely the Picard group of our set of valuations, which we can identify with this adelic quotient. And finally, since our torus T splits over L, from the statement for the Adel group, we deduce the corresponding statement for the torus. Okay, so why do we do this? Well, the point is that if we then set E to be the intersection of the principal Adels with the integral Adels, then one shows by a small direct computation that the Tate-Shafarevich group is contained in the image of the natural map arising from the embedding of this group E into T. And why is this good? Well, the point is that this group E is finally generated, and therefore, by general properties of Galois cohomology, the first Galois cohomology group is finite. So why is this true? Well, this group E that we defined is nothing more than a product of copies of the group of S integers for this set V bar prime, which is a finally generated group by Dirichlet's unit theorem. And so therefore, the Galois cohomology group is a finely generated torsion abelian group, and therefore it's finite. Okay, so that putting this together with the reduction steps at the very beginning, this yields the fineness of the Tate-Scheffer-H group for tori over number fields. Now, the point is that this argument can be extended quite easily from number fields to arbitrary finely generated fields. Okay, so now suppose that K is a finely generated field, and we take a divisorial set associated to a normal affine model spec A. And so to make the argument work, we need two important results. First, so this is an old theorem of Pierre-Samuel, is that the group of units of our Z algebra A is finely generated. And then we need a statement which in full generality is due to Bruno Kahn, at least as far as I know. It's that the Picard group is finely generated. And so putting these two facts together into the argument that I outlined on the previous slides, we basically get the results, not just for number fields, but for arbitrary finely generated fields. So specifically, the argument shows that the global to local map for tori over finely generated fields with respect to divisorial sets is proper. Okay. Now, once we have this statement, a natural follow-up question is whether or not this set of valuations that we're working with is in some sense optimal. Or, if we could, possibly replace it by a smaller set. Well, if we have a finely generated field, then one thing that we can do is view it as the function field of a variety over a number field. And then for V, we can take the set of valuations associated with the divisors on that variety, rather than the divisors on a model. And it turns out that one can prove a statement of this form. So namely, let's take X to be a smooth geometrically integral variety over a number field K, and take V to be the set of discrete valuations of the function field associated with the prime divisors of X. Then we show that the Tate-Scheffer-H group is finite for any torus that is defined over the base field little k. Okay, so just a little bit of history. So this result was initially proved by Harari and Samueli in the case that X is a curve. Now, the most serious restriction here is that, well, we take our torus to be constant. So that is to say, it's defined over the base field little k rather than over the function field capital K. And at least as far as I'm aware, is that if we drop this assumption, so if we don't work with constant tori, then the fineness of the Tate-Scheffer-H group is very much an open problem, even in the case when X is a curve. Okay, so that's sort of the main restriction here. Well, if we're willing to impose some fineness assumptions on our base field, then it turns out that we don't have to make this assumption that our torus is constant. And the fineness property that is relevant here is Serre's condition F. So, which says that, well, a field is of type F if the Galois group has infinitely many finite, has finitely many open subgroups of index m for each integer m, or equivalently, our field has finally many degree m extensions for each integer m. And so these fields are actually quite common. So, for example, finite fields, p-adic fields, and more slightly more exotic things like Laurent fields of Laurent series over algebraically closed fields. So this is a fairly large collection of fields. And so then what we show is that if K is a field of characteristic 0 that satisfies Serre's condition F, and we take X to be a smooth geometrically integral variety over such a field, and V to be the set of discrete valuations of the function field associated with prime divisors of X, then the Tate-Schaffer-H group is finite for any torus, and now we allow the torus to be defined over the function field. And the proof of this statement uses some purity results for torsors, as well as finiteness properties of a topology. Okay. So that's what I wanted to say for tori. In the time that I have left, let me maybe say a few words about semi-simple groups. Okay, so first, since we know the properness conjecture for tori, a natural problem is to consider is to try to reduce the properness conjecture from arbitrary reductive groups to say adjoint semi-simple groups, at least over fields of characteristic 0. So far such a reduction has not been made, but it certainly seems plausible that something such an implication can be established. And why would this be good? Well, the point is that the properness conjecture for adjoint semi-simple groups turns out to be closely related to the analysis of groups with good reduction. And so in the last few minutes, let me briefly say what I mean by this. So first, a couple of words about good reduction. So suppose K is a field equipped with a discrete valuation V. So then we say that a reductive group, G over K, has good reduction at V if there exists a reductive group scheme over the valuation ring of the corresponding completion, whose generic fiber is isomorphic to the base change of G up to the completion. And so this model actually turns out to be unique. So therefore, one can talk about the reduction or the special fiber, which by general properties turns out to be a connected reductive group over the corresponding residue field. Okay, so this is, of course, somewhat of a perhaps a abstract notion. So let's just quickly look at a couple of examples. So first, any split group has good reduction at any place V. The point is that by Chevallier's construction, split groups arise over from group schemes over Z. Another example that's rather straightforward to describe is what good reduction looks like for the group SL1A. So the algebraic group associated to the elements of reduced norm 1 in a central simple algebra A. And it turns out that this group has good reduction at V if and only if our algebra is unramified. That is to say, it arises from an Azumai algebra over the valuation ring. And one more example that I'd like to mention is what good reduction looks like for spinor groups. So if we take Q to be an n-dimensional non-degenerate quadratic form, then the corresponding spinor group has good reduction at V if and only if up to scalars the form is equivalent to a quadratic form, all of whose coefficients are units in the valuation. And one more bit of terminology before I formulate the main result. So about K-forms. So recall that an algebraic group is called a K-form of our group G if this group G prime becomes isomorphic to G over a separable closure. So for instance, the group SL1A that we had on the previous slide is a form of the group SLN, again, because over a separable closure, a central simple algebra becomes isomorphic to a matrix algebra. And let me quickly mention for spinor groups. So of course, the spinor group of any other non-generic quadratic form Q prime in n variables is a K form of G. Now, if n is odd, then these are precisely all the K forms. But for n even, there may be other forms coming from Hermitian forms over non-commutative division algebras. Okay, so now let me finish up by formulating the precise conjecture for groups with good reduction, and then outlining the connection with the properness conjecture. So we take K to be a finely generated field via divisorial set of places, and G a reductive group. Okay, so then we conjecture that if the characteristic is good, then the set of K isomorphism classes of inner K forms G prime of G, which have good reduction at all V and V, is finite. Okay, so yeah, basically we're conjecturing that there are finely many forms with good reduction for over finely generated fields with respect to divisorial sets. And what is the connection with the properness conjecture? Well, suppose again K is a finely generated field via divisorial set of places. And recall that we're considering the global to local map. And so the connection turns out that if we assume our main fineness conjecture, so that is to say that there are finely many forms with good reduction. So if we assume that conjecture for a simply connected group and all divisorial sets of places, then it turns out that this global to local map is proper for the corresponding adjoint. Okay. So in other words, good reduction, or rather the validity of our main conjecture concerning good reduction, provides a uniform approach to the properness conjecture for adjoint semi-simple groups. And since I'm basically out of time, let me skip most of what I wanted to say about the properness conjecture and just finish up with this. So it turns out that conceptually, so the study of good reduction turns out to be very important in this evolving theory of algebraic groups over higher dimensional fields. So as I already mentioned, it has close connections to local global principles, specifically the properness conjecture. Unfortunately, I don't have time to talk about this today, but it turns out that good reduction is also closely connected to the genus problem, which deals with fineness properties of groups having the same maximal tori. It also comes up in the analysis of fineness properties of unramified cohomology. And one further connection is that good reduction arises quite naturally in the analysis of weakly commensurable Zariski-dense subgroups and applications to various classical problems on locally symmetric spaces. So the point is that although my main focus today was on local global principles, sort of more conceptually, perhaps the correct thing to look at is the study of good reduction, which already occupies a central place in the emerging arithmetic theory of algebraic groups over higher dimensional fields. Okay, so I think I'll stop here. Thank you.
Thank you very much. Are there any questions or remarks?
Is there any known result for split algebraic groups for local global principles? Or
Okay, so so concerning the properness conjecture, so let me maybe let me go back. So okay, so some results that we have obtained are that well, over arbitrary finely generated fields, it is known that this properness conjecture holds for example, for the group PSL1A. As I said, for arbitrary finely generated fields, this is still very much a work in progress, but we have obtained results for two-dimensional global fields. And so here's a list of some groups where it's known.
Hello, Igor.
Yeah.
Yeah, it was a beautiful talk. Thank you.
Thank you very much.